I'm getting no sound.
They haven't started yet. It's probably okay.
On. It was whoever changed the batteries.
Well, I make it 6 o'clock, so it's time to go.
Out the door.
Welcome to this meeting of the London Centre of Newcomen Society, and welcome to a slightly larger number online, I think, Dan. The meeting will be streamed and recorded, just a warning, and subject to the agreement of the speaker, and providing there's no sort of copyright issues and things, we will post that on the YouTube channel later if appropriate. To ensure we don't pick up any extraneous noises, we have had lots of those, both from people online and from people here, but usually from people online. Please make sure that those online are muted at all times and unless called upon to speak. We've had some interesting things around eating apples and things. It is rather distracting. So if you are watching, please use the chat button to put in any questions, and we'll pick them up in the raise hand facility later on. Those present, mobile phones on silent. I'll check mine in a minute, but please do that. And then we should have a nice, smooth environment for Peter. Now, we've not been informed of any fire tests, fire alarm tests and so on, so any alarm will have to treat as serious. Fire alarm signal here is continuous ringing. There are fire extinguisher and break glass points around, and they're not holding open the fire doors, so that's good. Fire exits located. The door most of us came in, and door over this corner here. And if we are asked to evacuate the building, then we meet by going out past the gallery into Cowcross Street, and we then turn right, I think, into Cowcross Street and down to Greenhill Rents, and we meet there at Cumulate. Please, can we go there if we have to, so we can check people off? One of the reasons we ask people to sign in, we always have an interesting situation in our meetings. The list of signatures and names on these lists never quite tallies with the count you do by going around the room. The strange thing is when the count actually is lower than the number of names on the list, but it's usually the other way around. But if people could please sign the list, that's great. Members, just a name and a tick to say you're a member. If you're a non-member and you'd like to keep in contact with, or us to keep in contact with you, please give us an email address. Right. Dan, you've arranged a dinner table, I think? Yeah. So there is a table arranged for dinner for some people to go out for dinner with Peter afterwards. Contact Dan afterwards if you want to do that. Okay, so this lecture will be given by Peter Filsack. I've known Peter far too long. Then I find that
Likewise.
I now find myself as president of the organisation and Peter is the honorary treasurer. So it's back to working in harness again. He's going to talk to us on the subject of failure of marine medium speed engines, of which there's a large catalogue to choose from. So I'll be interested to see what he picks out. Now, Peter worked most of his career at Lloyd's Register, which is a long time, in a department that's known as Technical Investigations. And that department was set up as long ago as 1947 by the then Chief Engineer Surveyor, Dr. Stanley Dorey, who wanted to understand why these things kept breaking, find the technical reasons, write rules and standards to try and stop it happening again. So Peter will present us with some interesting cases, I'm sure, and we look forward to some questions afterwards. Peter, over to you.
Well, thank you, Lloyd. You've just wiped out half of my introduction. I was going to explain what Lloyd's Register and TID was all about. As Vaughan said, I spent most of my working life working for Lloyd's Register. Now, if you're in the marine industry, everybody knows what classification societies are. If you're not in the marine industry, we're a very funny organization. Lloyd's Register is a classification society. It classifies ships. It makes sure the materials that go into ships are in accordance with well-founded rules and regulations, and they are maintained to a certain standard, otherwise known as Lloyd's rules. It's an odd outfit. We used to be a charity until 10 years ago. It's governed by a committee of the great and good in the marine world, shipbuilders, the engine builders, insurers. So they all make sure that all decisions are sort of fairly evenly handed. The Lloyd's bit goes back to the same coffee shop as Lloyd's Corporation, but we're nothing to do with the corporation. They do the insurance, we do the surveying. We do the hard work, if you like. The register bit comes from the coffee shop when, I think it was Edward Lloyd, published a register of ships that were classed, so that the insurers could take a reasonable punt on them not falling apart at sea, and the shippers could also take a reasonable punt on them not foundering. So and that has more or less survived to this day. If a ship is classed, you have a reasonably good chance that she's all right. There are four main classification societies around the world. The Norwegians have an excellent one, Det Norske Veritas. I must pay up. They are actually quite technically good. Rena, Germanische Lloyd were taken over by DNV and ABS, who look after their own interests across the pond. All the classification societies, the major ones, belong to an outfit called IACS, which is the International Association of Class Societies, which tries to ensure uniformity of the class rules around the world. I think the EU had something to say about competition law on this, and I'm not sure where that's gone. Into the long grass, I hope. Yes, this is Vaughan's still my thunder here, founded in 1947. Post-war years, quite a lot of development and research going on in British industry. Simon Archer, who was a Lloyd surveyor in TID, he investigated the Victory propeller failures. If you look at there's a nice chart somewhere showing the North Atlantic scattered with propellers, which fell off the shaft. He was instrumental in diagnosing the problem. Around that time, Parmatrada came into existence because the Royal Navy were less than impressed by the steam machinery during the war. They'd taken one look at the American equivalents and said, "Oh, we want some of that, please. It's much lighter, more efficient than ours." The BSRA, British Ship Research Association, was set up sometime after the war to provide fundamental research into ships. So TID was in a good crowd. One of the big things I differentiate TID from other consultancies was the ability to measure things. Measurement played a big part in our investigations. Perhaps not so much of these legend failures, but otherwise. Because until you can put numbers on it, you're just expressing opinions. I have been in meetings with ship superintendents and God knows else, and they've all got their own opinion to what's wrong. And until you actually bring out some numbers and say, yeah, this is what's wrong, you may as well forget it. Someone over there asked a very pertinent question. I said, why are we talking about medium speed engines? Because there's a lot of them around. Most ships will have 4 diesel engine auxiliaries. One will be under repair, one's under standby, and 2's there for taking the load duty. And you can be sure that one of the duty engines will fail as you're entering harbour or doing something, you know, it'll fail at the worst possible time. So 4's a good number. There's probably a 5th one around if you count the emergency generator. But my experience, emergency generators don't always work. So you can see the proportions of there's some nearly 40,000 auxiliary engines and 12,000 main propulsion engines. They are liked, obviously, for diesel gensets. They work at 400, 700 RPM, ideally suited for generating. But they're also liked for main propulsion because they've got low headroom. They're very compact. A medium speed engine is probably not much higher than this room, a little bit higher. And also, you can mount them on resilient mounts, which isolates the vibration. Passenger ship owners, cruise ship owners really like them. I'm not looking at someone. Ferry owners like them because of the low head height. You can get an extra, you can get a car deck low down on the ferry. So yes, they are quite popular. The other source of main propulsion is ships. In fact, probably most cargo ships, like container ships, are slow-speed diesel engines. Slow-speed diesel engines used to be about 120 RPM. They've gradually crept down to about 70 RPM, with huge shafts transmitting older torque. Slow-speed diesel engines can be anything up to 50 megawatts, 70 megawatts, powering a huge container ship. They are really big. They're as big as this building. If you go down the engine room on a container ship, you can't see the engine because it's there big in front of you. And slow-speed diesel engines have the edge in economy. They're up to about 50% fuel efficient, which means, you know, you're getting a lot of power for your money for the fuel spent. My background is perhaps more steam than diesels. I quite like steam power. Nice, smoothly rotating machinery, none of this walnut crunching of systems going up and down. But you're never going to get a steamship more efficient at about 35%. So, you know, they've just gone out the window. Apart from a resurgence a while ago of on LNG ships when they were burning the oil off from the cargo. So we'll have a look at some of the failures. This won't take long. I felt it was quite an idea to give you some idea of what we're going to talk about. Slow-speed diesel failures, totally dominated by turbocharger failures. Turbochargers are high-speed machines with very fine running clearances, running at high temperatures, sitting on top of an engine which doing its best to break loose from the chocks. It's not a very friendly environment at all. Next down on medium speed engines are crankshafts and connecting rods, which, you know, they're major components. Looking at crankshaft defects, very odd this, the main defects are on the main bearing assembly. That's the main housing keeping the crankshaft in the entablature. Less so failures of the pin, and it's odd that the failure of journals is somewhat less than the failure of the main bearing, considering they're part of the component. I guess it's probably because the bearings are doing their job in sacrificing themselves. Looking at the connecting rod defects, it's nearly all the bottom end. Yes, got that right. Bottom end, that's a bit of a connecting rod that connects to the crankshaft, otherwise known as the big end. That totally dominates the failure of the connecting rods. Right, now we come to hopefully some pictures which will keep you interested. TID provided technical input into the rules and regulations for Lloyd's. we're fairly instrumental in providing knowledge on some things like the last one I think I did was shaft alignment. We also helped out on noise and vibration and measurement of torsional vibration. But most of the work was for owners. Very little work for shipyards because ships under warranty at that stage. Owners have problems and they want somebody to come along and say what the problem is. Quite a lot of, I'm careful not to slang, a lot of chief engineers are very good, a lot of superintendents are very good, but a lot of them working at the limit of their knowledge of this sort of thing when a failure happens. They're very good at running day-to-day stuff, but when a big failure happens, you've got to pick up the phone and get somebody to talk to them. So a lot of our work was carried out for owners. Usually, the owners had their eye on us providing them a report that they could take along to the insurers and say, look, it wasn't our fault. So let's go through this now. I should have said, most medium speed engines are operating 400, 700, 1,000 RPM. Pin diameters, 200-300 millimeter. Most of them have this design of bottom end bearing for the connecting rod. It separates there in the middle. That allows the engineers to pull the connecting rod out through the top end of the engine. You don't have to disassemble the bottom end bearing. That's very, very handy for medium speed engines because there's a lot of maintenance work on them. On this one, there's 4 bolts holding the bottom housing for the connecting rod, which failed. This thing here in the middle is a compression shim. They wanted to get a bit more oomph out of the engine, so they added 0.5 millimeter or something to give it a bit more squeeze. This particular engine was fairly standard, 8-cylinder engine, about 5 megawatts at 510 RPM. The engine had just undergone repairs for fretting damage to the entablature. Now, diesel engines are susceptible to fretting. Fretting is the bane of a diesel engine. You've got to keep on top of it because there's all these components in a diesel engine with explosions going on in the pistons and cylinder, wanting to tear the engine apart. So all these components are rubbing against each other and setting up fretting. Fretting is very dangerous for reasons I'll show you later on. I've got a very good slide showing the consequences of fretting, or initiation of fretting. This engine, as I said, not long out of overhaul. We did checks on recommissioning, started up, ran it for 8 minutes before a loud bang was heard. Now, 8 minutes is a bit of a long time to go around and check for overheating bearings and failures. You know, a couple of minutes would be more like it. This slide, I put this one in to try and illustrate the connecting rod. This whole assembly from left to right is probably no more than 2 meters, 3 meters long. Piston, gudgeon pin, connecting rod, and this large housing at the bottom end bearing. And in the housing are thin wall bearings. These are thin steel bearings overlaid with white metal. The old days of having big, heavy cast white metal bearings have gone because they had pretty awful fatigue strength. These thin wall bearings are much better in this respect. But they take up the shape of the housing. So you've got to maintain the shape of the housing, as I'll talk about later on. We took the bits back to our laboratory. At that time, it was in Croydon. The 2 bottom end studs, which held the cap on the lower half of the bearing cap on the right, the nuts were in about the right position. On the left, we found they'd run down to the end of the studs, and there was hammering damage underneath them. Well, obvious thing is they've not been tightened up. However, the engine repairers swore black and blue that they had done, and they produced the evidence from their notebooks that it had been tightened up. But you know, you can't argue with something like this. This is another bottom end bearing. This is a bearing shell, thin wall bearing shell. It's suffered from fatigue damage. I was about to say it's easy to see that it's fatigue damage, but only for the experienced eye, I guess, if you've seen it. It's got the bits of white metal have come out of less sharp edges. It's where the metal is flexed underneath and the white metal is pinged off, if you like. This really concerns quite an old engine. And one of the questions you sometimes get asked is, what sort of life do these engines have? And I would say, providing you keep them everything within manufacturer's tolerances, you can keep them going for ages. Keep on top of the fretting, keep bearing clearances within reasonable tolerances, and you can keep going. On this particular engine, that bottom end bearing shell had worn out of shape. It had become lemon shaped. It had become that shape, big on the side diameters and small top. Here again, the engineers had an emergency alarm go. All engines have a crankcase oil mist detector, which if the bearings are misbehaving, sends out a mist, and you sniff it, and being the alarm goes off, you should shut the engine down. However, the engineers on this looked at it, said, oh, not a problem here, started it up again, and it went bang. So, you know, always trust your instrumentation, nearly always. Trust what it's telling you. However, I think there is another case later on where they also ignored it, but I can see why. This shows the back of a bearing shell, and the slide is included because it shows fretting damage on the back of the shell, and it's something that I always tell my colleagues to not only look at the damage on the running face, but to look on the back faces, the mating faces, because they'll often tell you as much about what's going on as the running face. And in this case, you can see where fretting is occurring, which has led to a gradual relaxation of the shell. In this case, it was quite the ovality had increased about 0.16 of a millimeter, which is sort of a similar size to the normal bearing clearance. I mean, you can't sustain a good oil film in this, and that's what this engine failed on. Failure number 3. I'm afraid this is all failures coming up, so I hope you're going to be interested in them. This is another 4-stroke engine. In fact, all medium-speed engines are 4 strokes, except for some recent ones. This has got a slightly different design of connecting rod, because this was operating at about 1,000 RPMs. A slightly different design here to try and keep the mass of the big end down, keep the inertia load down. Because this thing's whizzing around at 1,000 RPM. You don't want to have too much inertia there loading the bearing up. Again, the engine was in the middle of the sea, shut down, opened it up, and found an unusual failure across here at the base of the connecting rod. We retrieved the parts and identified fatigue damage. It was fatigue. A lot of failures are caused by fatigue. Fatigue is not difficult to identify, but usually there's no gross distortion. If you have an overload failure, tensile overload, it'll be pulled apart. You can see the classic necking. Fatigue has very little deformation, and usually you can see the classic breach marking where the crack has advanced in stages. People have tried to count the number of rings in the beach markings with dubious success, I think is the best way to say it. And I'll come on to that later. We identified the origin here and took a closer look at it and found the thread had been heavily gouged. Right. With highly loaded components, you want nice, smooth surfaces. You want them smooth. Well, radius. Here, someone had run a stud in and gouged it, which is great. If there are either crack initiation site for fatigue cracks, it will break eventually. We looked into this one a bit more. And, you know, I said earlier on that classification societies, one of the roles is to provide a traceability for parts from manufacturer through to installation on the ship. Well, when we asked the chief engineer and superintendent about the studs he'd fitted, it became very vague, and there was definite lack of paperwork. And we surmised these studs had come from a grey supplier, shall we say, which weren't within the manufacturer's tolerances. On top of that, when they overhaul the engine and fitted these studs, they should normally just run in hand tight. Don't need any tools, bit of oil, and they should run in. Whoever fitted these studs must have really grounded and used some force to get them in. You know, it was obviously a problem, but like a lot of fitters, you know, they want to get the job done and get home and have a beer. Earlier in my life, I spent a summer working in R.H. Green's Scilly Weirs. You used to have a ship repair yard right underneath where the airport is now, London Docks. They were past their best then, which is saying something. I arrived there, and first thing the shop foreman said, if he touches the tool, we're out. So, but I went out with the outside gang working on the ships, and I probably learned how not to repair ships' machinery with them. It was an interesting experience. For my other summer holiday, I spent working for Merley's Blackstone, Hazel Grove, 3 months, doing a rushed apprentice, and that was incredibly good. That's of all the things I've done in my life, that probably has stood me in good stead. Probably as much as my training, the Lloyd's Register, where I spent a year in Rotterdam, that was really good. This is another auxiliary engine. This is something you really don't want to see when you come down to the floor plates in the bottom of the engine room and see what it shows here is a balance weight that's come out through the side of the engine and the crankcase door. The story behind this one is this engine had been in service for a long time, 90,000 hours. You don't really expect fatigue problems at that number of hours. Lloyd's Register had issued a noteworthy survey item when these engines were new to bring attention to the possibility of failure of these balance weights. So had the engine builders. It was a known problem, but any failure should have occurred very early on in the running life. So this was a bit of a mystery. That shows a hole in the engine where it came out. It's interesting because that's probably repairable. It's not a stress component there. you can metal lock it. And metal will tell you, company will tell you they can metal lock anything. Well, perhaps not highly stressed components, but they will try and do it. It's a drawing of the balance weight. The crack had initiated here at the end of the red arrow. When we opened took the bits back to the lab, and TID's material lab plays a big part in this. We had a very, very good metallurgist called Colin Wayland who'd come from Paxton, and he had an uncanny ability to section things at the right place to identify the origins. Again, it's clearly fatigue, nice clean fracture, beach marks propagating radially outwards. What was surprising when we had a closer look at the crack was micro cracks associated with flame cutting. This sort of causes us to draw breath a bit. You know, you don't really want flame cut components on balance weights, but that's the way they've been built. And I think the engine builders had intended to machine them all out. Had intended to. They hadn't got them all. Closer look at, found there was a dirty area of the crack, about 2 millimeters deep, just right below the surface. And it looked as though this engine had actually been running for quite a long time with this crack. This crack had filled up with dirty oil. So again, how? Why? To try and understand the problem a little bit better, we constructed a finite element model of the balance weight. And not unexpectedly, the highest stresses are in the corner there where the crack occurred. But the predicted stresses is only something like, can't read it too small, 114 newtons per millimeter squared. It's low. You could guess, and that's at the stress concentration. That's including stress concentration. Now, that's much, much lower than a typical fatigue strength of mild steel, which you'd say is 200, 220, 250. It's a bit of a guess, but so we wouldn't have expected it to have failed. Most fatigue theory, most fatigue descriptions, a lot of it is descriptive. People do tests. Remember the original Vola tests they did in Germany on railway axles? It was always put them in, see how long they go for before they break. Lots of people did lots of experiments on different materials to find out how often, how far you could bend a bit of steel at what stress level, how many cycles. And it's a very useful shorthand, if you like. There is another way of looking at fatigue, which is fracture mechanics, which is very clever stuff. I think the guy who started it off was a chap called Griffiths in the 1920s. It was way ahead of his time. I mean, we're only just coming to understand this, look at this in the 60s, but Griffiths was really a clever chap. And basically, when you look at a fatigue crack, the surfaces are opening and closing like this. And if you open and close them enough, at a high enough stress level, the crack propagates. Now, there are several clever things you can do with this crack propagation. When the crack propagates across the grain boundary, it releases energy. You can listen out for this if you're good enough. You can put sensors on a bit of kit, item that's suspected. You can triangulate, locate where the crack is. You can tell how fast it's failing. You can even take photographs, thermal imaging, showing release of energy. It's something that was getting there a bit at the limit of my calculation abilities, but one of the things, the characteristic of fracture mechanics is it's postulated, and I think something called Paris's law. But there is a critical stress crack size beyond which a crack will not propagate. The stress is low enough and that crack size will stay there. It won't propagate. It's how the airline industry manages their fleets of aircraft. Most aircraft are made of aluminium alloy. Aluminium alloy has an absolutely terrible fatigue life. But it doesn't have a fatigue life. It just keeps on going until it cracks. So you monitor the aircraft for cracks. You keep them within certain lengths. If they propagate beyond, say, 5 millimeters, you change them out. You should cut out the part. CGB used to have the same problem on their big turbine rotors. You know, the power stations had absolutely huge rotors, and it's very difficult to make a forging that size without defects. But providing you know where the defects are and the size of them, you monitor them and make sure they don't grow catastrophically. Which is why a lot of the big power stations in the UK were on base load, because you don't want to run these machineries up and down through up to service speed to 3,000 RPM, because there will be resonances, there will be high stresses in that run up. So keep them either at stationary or at load. You don't start, as soon as you start shifting them to generate the high electricity at the peak hours, the generators are out of this, finish, which is basically what happened to the big power station in the UK. Anyhow, coming back to the story, a bit diverged there. We calculated that the critical crack size of this engine on this balance weight, oh, sorry, wrong one, was 2 millimeters, which, uncannily enough, was about the same size as what we'd identified in the metallurgy. I promise you, we didn't work backwards to get what we want. It was sheer coincidence. It was. No one could have been more happier than me when we identified that. But the problem was, why had it happened? Why had this crack, which had been dormant for 90,000 hours, suddenly propagated? We went back on board, probably did what we should have done earlier, looked through the logbooks, talked to the chief engineer. I said, what's been unusual about this engine? He said, oh, we dropped a valve about 400 hours ago. Dropping a valve, colloquial term. One of the valves fell into the piston, into the cylinder, smashed the top end. Lots of cooling water went in and stopped the engine like that. So what I think happened is that was enough, that sudden stop was just enough to propagate the crack to 2.1, 2.2 until it started growing again. Quite unusual. I can't actually prove it, but it seems to fit the facts. This is a bit more of a sort of humdrum problem, but no more interesting than for that. Ship repair work is notoriously difficult and dirty. But there are occasions when you've got to be clean, working inside engines, working inside gearboxes, for instance. I've done work for some Japanese gearbox manufacturers, and they won't let you go near the gearbox with anything in boiler suit pockets. You have to empty anything out before you look at, that's good. You don't want rulers dropping out, pens, spanners dropping down into the gearbox, because it's quite often very difficult to get in there. There's usually an obscure manhole somewhere in the bottom which is full of oil. And on this case, this was a ferry where they'd been in dock for repairs to the propeller shaft, and they'd taken a chance to open up the gearbox to inspect it. Started up the engine after repairs, did a dockside trial, gradually increased the speed until very quickly a loud bang was heard from the gearbox. Quickly shut down. We were lucky, we were on the spot on the ship very quickly. In fact, as they opened the gearbox up. and retrieved these bits from the bottom of the gearbox. On a closer looking at them, we found that they were chrome vanadium steel with stampings on saying brittle, which was just like this spanner there. Obviously, someone fitter had been inside the gearbox, put it up on a ledge to get out or something, just totally forgotten about it. It went through the gearing mesh very nicely, left a band of damage about 50 millimeters wide all the way through, which we advise, dress it up. It's not a problem, providing you take the load off that bit of the tooth. Maybe 50 millimeters and a face width of 1,000 millimeters. Well, 10% reduction in face width, 10% reduction in torque. And because of the way the propeller law works, come down 10% on torque, you're not going to lose an awful lot of speed. However, the owners wanted to maintain full service speed, which I don't think we ever did before this, but they managed to get a new gearbox out of the insurers, which was fine. This coming back to bottom end damage again. This shows the upper cap of a bottom end bearing. This was quite interesting, in as much not so much for the technical side, but the administration side, the certification. These were engines which were part of a very large order. I mean, sort of, some of them with a Lloyd register class, some with BV, some with DNV. It was quite a significantly big order for the engine building industry. They're all 8-cylinder engines doing about 3.5 megawatts at 720 RPM. They're auxiliary engines. I'll probably say what sort of ship because that will identify them straight away. We had 3 failures very quickly in the service life. One 300 hours, 1,600 hours, and 1,800 hours. That's, that's very quick. Something is wrong. We wanted to go in and look at the engine builder's factory and shipyard. There's a lot of procrastination going on. I suspected quite a bit of wondering where all this was going to lead. We got one of the rods back to the lab and examined it carefully. This shows the surface of one of the rods. This is magnetic particle inspection, showing cracks. Magnetic particle inspection is very good. It's very sensitive. It shows up very small cracks. And there's lots of them here. When we section the head, again, my colleague Colin Whalen knew exactly where to go. This is what we found. Forging laps. Lots of them. Very, very fine cracks. Now, in conventional fatigue theory, most of that fatigue life is taken up with propagating the initial crack propagation phase. Once you've formed the initial crack, it doesn't take long for it to go to full length. So if you have an item of machinery with pre-existing cracks in like this, you're going to fail. It's got very little fatigue life. The closer we looked at these, there were lots of other defects. Poor finish, poor surface finish, local decarburation, excessive grinding. Somebody had used a windy hammer, a grinding tool, to try and dress out surface defects here. And the threads form inside the heads was very, very poor. If it hadn't failed from the forging laps, it would have failed from these threads. Because it's a large order, built for more than one classification society, and I think there were 3 or 4 owners involved. Getting all the paperwork together was quite an adventure. Most of it was good, I'm pleased to say. Some of it was a bit sort of, oh, where's that certificate? Oh, we seem to have lost that. But by the time we delved into it, it was apparent that the 3 failed forgings had come from the same forge, somewhere in deepest Eastern Europe. Now, the trail was quite interesting because the raw forgings had been taken to Korea, to the Far East, rough machined, shipped back to Europe for final machining, and then shipped back to Korea. You know, this is something that was quite novel, you know, quite unexpected. So we approached the engine designer, the engine licensees. Most machinery, certainly medium speed engines, are not built by the designer. They have a designer who licenses the engine builder to builders in Korea, UK, or wherever. It's their responsibility to issue the design. And then the engine builders will build in accordance with design, hopefully. And source everything, all the components off the licensor's approved list. Well, we went to the licensor with this. I said, oh, you know, how about it? What about these forgings? To which they said, oh, they were taken off our approval list years ago. And we don't understand how they'd got into the supply chain. Well, yeah, I think actually I believe them, but somebody has been shopping it. I can only think that there's such a large demand for these parts, a large order, that maybe some bits got into the supply chain that shouldn't have done. This is another passenger ship, a 12-cylinder V engine. Undergoing repairs, they opened up the units and found 2 units with damage. This gave the owners a sort of a bit, oh God, what have we got here? We've got 6 of these engines, I think, on the ship. Are we going to have an epidemic of problems? I'm going to have to cancel voyages. So we had a good look on board. That shows the underside of one of the cylinder heads, the flame deck. Totally destroyed there around the injector. That was one of the valve heads. We couldn't tell anything. That had been in a cocktail shaker for too long. It totally damaged any evidence. However, we did pull out the valve operating spindle. Yeah, and it had failed in fatigue. As you can see, there's fatigue origin somewhere up here, beach marks going down here. It had gone 90% of the way through before it finally failed under overload, and that's not uncommon. We also looked at it, and it was not straight by a long way. So what I think had happened, that the repeated closing of the valve springs kept pulling the rod and propagating this crack. But why? Well, one of my colleagues who drew the short straw on this went on board and sifted through all the bits of the engine. Which, if you've got an engine failure, you've got to do that. A lot of the time, the chief engineer has got to keep the ship going. So you'll clear up all the parts off of floor plates and put them in a couple of big plastic dustbins, which you're then presented with. You take this out and where's that from? The better ones will take photographs of the failure before they move anything. That's quite good. We'll even take photographs of the control panel, which is, again, helpful. My colleague looked through all the debris from this engine, looked at one of the lube oil supply pipe to this cylinder, and the proverbial rabbit pulled out a bit of cloth. We think that was enough to restrict the oil supply to the valve and cause failure. Certainly, any failure of restriction lubrication is not a good thing. The other cylinder head wasn't particularly damaged. Well, was not gross damage, but there was cracking between the valve inserts and the injector in the middle, which again is not good. It's going to fail at some time. That was a bit easier to diagnose because we took the valve inserts out and found the cylinder head was full of oil, fuel oil, that had a leakage of fuel oil into the water cooling system. So it wasn't being cooled, it just overheated. So we were quite happy to tell the owners these were two unrelated problems and they were unlikely, famous last words, to have any further problems. Now, this is interesting, I think. Earlier on, I said that magnetic particle inspection is very sensitive and is a good thing to use. On the other hand, dye penetrant takes a much better photograph. On this, I always think this is a good photograph. It shows a journal on a medium speed engine, again off a passenger ship, where I think there was a diesel electric installation. It had 6 engines driving electric motors, which is a good design. Gives you flexibility, redundancy. It's quite a big engine too. This is 6 megawatts. When you see a crack like that at 45 degrees, it's torsional failure. Nothing else. On most shafting systems, the torsional stresses are the highest by a long way. Axial stresses, usually negligible. In fact, it's very difficult to measure axial stresses. Bending stresses, yeah, maybe 5% of the total, but shafting systems, marine shafting systems, are dominated by the torsional stresses. That rules the size of the shaft. Again, this engine had run for about 50,000 hours. No apparent reason for it failing at 50,000 hours. We checked the torsional vibration calculations. All reciprocating engine installations have their torsional vibration calculations done, because all shafting systems will vibrate torsionally. The trick is to get the resonance away from the operating speed range. Well, with gensets, it's easy. Just push the torsional resonance out of the barred speed range, or else you pass through it very quickly. So we looked at the TV cap, no problem. Looking at the crankshaft in greater detail, we found these cracks here and circumferential rubbing marks. And looking at the crankshaft, we opened the crankshaft up. This was quite a big crankshaft, so cutting this open was no mean feat. And it showed fatigue cracks from 2 origins, propagating here and here with beach marks. Not too long time to failure, was failed quite quickly. Stresses are quite high. In the fillet radius, where a cracking had occurred, we found overheating and thermal microcracking. Oh, these small cracks are a great crack initiation point. Overheated layer was, I don't know, I should have said a few millimeters. The top layer, not very deep, millimeter or 2. We took the bearing out. And this is the back of the bearing, the mating side. And when we looked at it, it was obvious that the bearing had ratcheted along the housing. It had started walking, if you like, from where it should have been into the fillet radius. And it eventually contacted the fillet radius, rubbed, initiated a crack, which led to the failure. A little more interesting, we couldn't, trying to match up the failed bearing shells and the housing was interesting because we couldn't quite make everything meet up. There were marks here, marks there, but they didn't correspond. And we suspected that these overheating had occurred before, but they got away with it. Maybe the overheating had allowed the bearing shells to relax and started them walking. Interestingly enough, this was a large passenger ship run by quite a large company, and the lube oil treatment was appalling. They were running the centrifuges at about 10, 15 degrees lower than they should have been. They were trying to put twice as much oil through as they should have done. And when the filters blocked up, they had full bore return to the crankcase. And you generate a lot of dirty oil in diesel engines. You need to centrifuge, you need to keep it clean. The rest of the bearings of this engine were quite dirty. We showed a lot of abrasive damage. So yeah, keep your oil clean. Coming up to the last one now, I'm probably glad to know. This is another bottom end of a typical, not the typical one, this one was a one-piece rod. It had failed across the shank here. Interesting. It was a single origin of failure. It had one point of origin there, a beautiful, you couldn't have a better illustration of fatigue crack than that. And again, as I mentioned earlier on, this crack has propagated all the way through before final failure. You know, it's not untypical to see fatigue cracks propagating for 90% of the surface. Again, we looked at the back of the bearing shells. It looked like this. This is fretting damage. This is movement of the housing of the shell within the housing. Because the engine was getting a bit old, the clearances were getting a bit high. But the real reason I included this, because when we looked at the surface of the connecting rod, we identified this fretting damage, these micro cracks associated with fretting. This is why fretting is dangerous. You can often see fretting on steel components. It looks like the red rust seeping out of the mating surfaces. On diesel engines, you can see the surfaces may be a bit rough and uneven. But if you see it, you've got to do something about it. And here, this is a classic crack propagation at 45 degrees from fretting on the surface. It plucks bits of material out and cracks propagate. It's not very deep. This is only about 0.15 of a millimeter deep, but it's enough to do away with your fatigue life. The item will fail. Okay. You might be, that's the end of it. That's the end of these horror stories. I found them interesting at the time. The talk originally grew out of a request from a shipping company to go and attend their annual meeting, shoreside meeting with ship's chief engineers and superintendents. They wanted somebody to come along and discuss some of the problems they had on board the ship and somebody to keep them awake after lunch. That was the start of this.
Julia thought I
1 hour flat. Good.
do some questions for you, but I'm not going anywhere near that. I know too much about some of those. So we'll take some from online when they come, but otherwise I'll wander around with this and you can all quiz Peter. One of the things that I do notice when I look through Newcomen Society back numbers of transactions and things, there are very few papers on what I would call things that went bang in the night and gave people a bit of a hard time. It's interesting because we always used to do an awful lot with the professional institutions that were dealing with the lessons you learn that you hope you don't repeat. So,
Thank you very much for a very interesting talk. You didn't mention any of the engine manufacturers once.
Oh, of course not. But if you buy me a pint round the back,
Could you comment at all on wear metals analysis? Because you sort of touched on it.
yes, it is carried out, and ship owners have quite some owners have a regular routine of sending samples back for analysis. British Rail, in the days before privatization, used it extensively on their diesel engines. In a big way, they monitored all their diesel engines. In fact, touching on British Rail diesel engines, I said most of four-stroke medium-speed engines, high-speed engines, are four-stroke. At the moment, the vast majority of freight engines on British Rail are two-stroke medium-speed engines. These big things that hurt the rail on freight trains are two-stroke engines. Whoever's done that has solved the great problem of breathing, of how to get air in and out of a fast engine. It's not a problem on slow-speed engines. You're only doing 120 RPM. The cylinders are going up and down like that. You can get the air in and out, charge in. Bit more difficult on four-stroke engine, on medium-speed engines, which is why the four-stroke, because you need to have an induction cycle followed by a squeeze and a bang. So whoever's designing a two-stroke medium-speed engine is great, because that means you get every cylinder has a firing stroke every revolution. You get twice as many bangs per kilogram, if you like. Sorry.
Thank you, Peter. A couple of questions. One simple and other sort of
the simple ones are usually the most difficult.
Unless I missed it, I think you were just talking about merchant navy ships.
Yes.
And I wonder if you might sort of say something about these sort of problems in Royal Navy ships.
I can do.
And the other question is, you sort of semi-apologize for dealing with failure. Now that you shouldn't apologize at any level for dealing with failure, because failure is really, really interesting. You can learn an awful lot more.
It's a way to learn
from failure than you can from success. And I'm wondering, did you, in your reports, feedback to manufacturers, to owners, etc., saying this is why it's failed? Find a way of fixing it. And are there any sort of areas where you show where what you discovered actually sort of had an effect in
we usually had quite a good working relationship with the diesel engine builders. The German ones are very good, the British ones exceptionally good. The one exception was Caterpillar and MTU in Germany, who kept the doors shut. They took the failed parts in there, pulled the doors, and then a new engine emerged. That was hopeless, finding out what was going on. Yes, as soon as we'd issued our report to whoever we were working for, usually the owner, I said, copies went to the engine builders, ship builders, God knows who else, to the insurers. We were quite heavily involved with engine builders. They wanted us to tell them, and we needed their cooperation sometimes. So it was quite a good relationship. On the question of the Royal Navy, we're two entirely different organizations. Merchant Navy overhaul their engines at sea, you carry engineers, you keep on top of your own maintenance at sea, you open things up for survey, you do it all on board. Now, before I joined Lloyd, I worked in the Northeast, building boilers, power station boilers, big ones. And I joined the Royal Naval Reserve there because they went away to sea at weekends, so it was good fun. And I enjoyed navigating. But my introduction to engineering there came as quite a shock. I said, what do you do about maintenance? To which I was met with a stare and a blank look. We don't do it. We wait until we send the ships in for refit. So yes, it's a totally different approach in the Navy.
Take that one stage further, Frank. The difference is a merchant ship makes money when it's moving. So I remember talking to one owner because he wanted to stop doing boiler surveys every 5 years or 2.5 years because the ship didn't stop long enough. So a container vessel was running, the plan was to go 10 years between dry dockings, and the longest stop was 18 hours. Now, warship only ever runs full speed when it's chasing something. So if you look at the gearbox failures, the Straths, P&O Straths, ran the gears after about 6 months or a year in the 30s. The Shiny Chef was chasing the Bismarck when it ran its gears. Several years later, but it was the first time it had run at full speed for any length of time. So there's a different operating regime, I think, that is quite dramatic.
Yeah.
They still break things.
Yeah, but at risk of being rude to the Navy, they didn't actually put a lot of sea time in, which is why naval vessels were quite subject to quite a lot of collisions because they weren't keeping a good lookout. Like this one frigate, Norwegian frigate, who went up the fjord and promptly smashed into a tanker. You know, the guy wasn't keeping a good lookout. Yeah, it's just a different regime.
Okay. Anything online, Dan?
Yeah, we've got a question online from Phil Healy. If he'd care to unmute himself and ask his question, or if he'd rather I could read it for him, one or the other.
Whatever's easiest.
Yeah, hello. Yeah, can you hear me?
Phil's opened his microphone, so if he'd like to ask his question.
Yeah, thank you very much for the talk. Some very interesting horror
Don't
stories.
seem to be hearing you, Phil.
You can't hear me. Any better? Hello?
Ah, right.
Any
Well,
better?
I think we've probably got some. We're experimenting slightly with a new setup here, so we may have found ourselves in a bit of trouble. I'll just read Phil's question. He asks, what rough proportion of failures would be attributable to design errors, manufacturing defects, or operating problems? Did you have a breakdown between those?
Off the top of my head, without looking at the failure statistics, I would say fairly evenly handed. Design takes a problem, yes. Operating errors, certainly. Manufacturing errors, sometimes. We had a case of a series of engines being built. I think there were 8 engines involved, and the first one went on trials, and the connecting rod failed. We looked at it, and they'd machined a sharp notch in one of the mating surfaces. Unfortunately, this was a CNC machine had done all this. So all 8 rods in 8 engines had the same defects. So machining defects, yes. You can see some of the ones I've shown of poor thread form. Operating defects, maybe not so much. There's certainly a tendency sometimes to overlook the crankcase oil mist detectors. But again, if it's a propulsion engine, it'll fail probably when entering harbour. And there's a great onus to get the engine back on load. You know, if you're heading for a dock wall, you know, you wreck the engine rather than wreck the ship. So no, I don't have the statistics, but off the top of my head, I would say fairly evenly divided.
Right.
Says, thanks for the fascinating session. I'm usually the techno idiot. He says.
Just speak into it, can I?
Makes a lot of room for.
Yeah. I just have to say one thing about Griffiths. It is a myth that he contributed much to fracture mechanics. He did some work on glass fiber around about 1926 or so,
Yeah.
and did show that you needed a critical crack size. After that, he did absolutely nothing. That, as far as I know, fracture mechanics began to take off in the 1940s with the brittle
Yes, indeed. The
the-
T2 tankers. Yeah.
the ships breaking in half, then with the Comet, and then British Gas, of course, with its concern about pipelines and hearing that a crack 8 miles long had developed in an American pipeline, put a huge amount of effort into fracture mechanics.
Yeah.
But Griffiths himself, I'm afraid, is rather overrated
Okay.
on both the jet engine side and the fracture mechanics side.
Okay. Thank you, Fred. I didn't know that.
But there's a very good book on, a very thick book on fracture mechanics, which I used to know the title of. And basically, you know, Griffiths is about 3 pages, and then you have the rest on real work.
My standard reference was.
I can't remember.
Yeah, my standard reference was Marsh.
But I have
Nelson,
a question. I was very interested. You know, this is when you came up with talking about Griffiths. This crack, which was the ship had run for 90,000 hours.
The 2 millimeter crack in the submarine.
And from what I understood, a small fatigue crack had been there for quite a long time.
Yep.
And then it was the dropping of the valve that pushed it over the edge.
Yeah, started. The stress was just high enough to start it propagating, I think.
What I didn't really understand is why you'd got that initial cracking in the first place. Have you any ideas about that?
The engine builders knew all about this. When the engines were new, they'd manufactured the balance weights by flame cutting, which we identified as small cracks in the flame cut surface. They thought they'd cut all the flame surfaces out, but they hadn't. They also issued inspection notices for ship owners and Lloyd surveyors to go and inspect these balance weights, which involved basically looking on the end of a balance weight and trying to identify a crack several millimeters in the middle of a balance weight. Absolutely impossible because you've got the connecting rod webs next to it. You can't do it. It was a piece of nonsense.
Yeah, I know. Yeah.
On that particular ship, I think it was an auxiliary engine, 4 engines, probably 8 cylinders. A sister ship, we took them all apart, found 2 more cracks, and got the engine builders were strong-armed to supply completely new balance weights, which were machine cut. Yeah. Yes.
Thank you very much. I think earlier in your talk, you mentioned Merleys. I used to work there in the 1960s, which is an awful long time ago now, 60 years ago.
Yes.
So my knowledge of marine diesel engines is 60 years old, I'm afraid. However, looking at your work, I get the impression that large end bearings or large ends in general were the main problem.
Yes.
Was this in fact so? What you scarcely mentioned pistons or cylinder heads or things like that.
Pistons and piston rings were renewed on a fairly regular basis, and didn't entirely wreck the engine like bottom end bearing failures do. I think it came out of the failure statistics. Now, those failure statistics were put together from Lloyd's Register's statistics. Now, one of the great things about Lloyd's Register is it has surveyors in every part of the world issuing reports, inspection reports, survey reports. They all come back to London and all the failures are put into a huge database, which very few people use. It's a tremendous asset. There's occasional awkward people like me come along with material and say, what are the failure rates on medium speed diesel engines? And at the earlier part of the talk gave those statistics. I passed through Merleys in about 1970. The chap in charge of a training school was a really excellent chap. I can't remember his name now. He taught me a lot. And later on, the Merleys technical director, I can't remember his name, must have been towards the 80s, was he initiated a lot of research in the UK. So yeah, I've got a fond spot for Merleys, even if some people haven't.
Well, I I did my PhD there, so
into what? May I ask?
Well, surprisingly, cylinder heads and pistons.
Oh, there's always going to be someone who knows a lot more about it than me.
I also did some work on large end bearings and failures. In fact, the failure of the bolts that hold all the two parts together.
Yes.
And at the time, I discovered that something called the British Internal Combustion Engine Research Society,
Yep.
had published a report on the failure on the stressing of these bolts. And I thought, oh, that would be interesting. So I sent for it. And all the firms that had replied had told exactly how they did the technical assessment of the stress levels and so on. Except one company, Company D, I remember it was, whoever that was, who declared that they ensured consistent stresses in their bolts by using a spanner of known radius and a hammer of known weight. And that is quite true.
Yeah, that is another story that in the marine industry, use of a flogging spanner, a spanner with a rope and somebody with a big hammer hitting it, of tightening up bolts. It's a load of rubbish. It's inconsistent. It doesn't work. It's far better to use hydraulic tensioning. If anybody says of flogging up nuts, forget it. It's not good. It's unreliable. I remember Merleys, the chap I was referring to, was having bottom end bolt failures, and he asked us if we could measure high frequency vibration on their engines, because he thought there might be a vibration component involved in these bolts. Well, we tried very hard, but on a diesel engine that's in service with lots of detonation noises and other noises, we tried and failed miserably. The only good thing about that job was we were up in a tanker operating. She was in North Blythe up in Northumberland, and the old man, he went out on sea trials, and a bit of a sea was running afterwards. And North Blythe Harbour faces is almost parallel to the coast. Northeast coast has not got much shelter on it, and I thought, well, we're not going to be able to go back into harbour. And this captain, he said, just watch this. And he put the lever down to full ahead, shot in through the breakwaters, just a superb bit of seamanship or nerve.
A little story, not necessarily to do with marine engines, but to do with testing engines. A friend of mine flies a de Havilland Chipmunk, and the engines have a finite life because the RAF tested them for God knows how many hours and couldn't break them, and said, oh, well, that's enough. The finite life is just how long we ran it for.
Yeah. The extra 100 hours.
A large number of marine diesel engines that have been taken out of ships that have been pulled up beaches in Bangladesh, Pakistan, and India that are powering Indian villages.
Yep.
And goodness knows what life they've got on some.
Yeah. Yes, they do get recycled in India. That's quite.
Any more online, Bill? No. Any more questions here? Have we drained the subject? Thank you for your time, Peter.
Thank you. Yes. Oh, glad that's over. I never. I'm never sure who's going to come along with the expertise that I don't have, and ask them.
I hope you found it interesting. It's a different sort of lecture to some we have. Who knows? Anyway, that was good. Next month, we have a different lecture again, which is about Rochester Bridge. And it says here, if I'll put my glasses on, that it's by Sue Clark, who's talking about from the 19th century medieval stone through to modern steel. So it's the whole development of the bridge in Rochester. We'll be here on the 8th of November, usual time, and it will be online for those of you who fancy taking life a bit easier. But it's nice to see you here, so thank you very much for coming. Thank you very much to those online, and see you in a month's time.
Thank you for listening.